Assalamu alaikum and a very warm welcome to everyone. I really hope that you guys are in a best state of mind to continue with geotechnical engineering lectures. As promised, today we're going to be discussing on or moving forward to chapter number 5, which will be focusing on slope stability. Again, this chapter is divided into two parts. The first part will consider the subtopic of E1 to E4, and the remaining two subtopic will be covered in part number 2. Now let's look at introduction. Now, in cases where the mass of soil has an inclined surface, the potential always exists for part of the mass to slide from the higher location to the lower one. It's just a tendency. Sliding tends to occur if shear stresses developed in the soil exceed the corresponding shear strength of the soil. This is when it's being explained in a technical context. You have shear stresses and also shear strength, shear stresses, and shear strength. This phenomenon is significant in development of highways involving cuts and fills, embankments, and earthen dams. So to give you a clear picture of how a highway is constructed along a slope area, there are two types of approach. One is cut and fill road, and two is full bench road. Now, how does the first one takes into account? So it has a normal slope, okay, and it cuts half portion of it, and then it fills on the lower part. So it has a cut and fill approach over here. And if you look at number 2, full bench road, another approach, you just cut the whole thing over here and dump the soil somewhere else, and you define the road over here. Okay, two types of approach for highway along the slope area. Now if you look at a bigger picture, you'll see something like this. Okay, initially the slope was in nature state. Okay, so all this was cut to make way for the road to pass by. Okay, so this is the reality at site. Now in today's context, we're looking into a more informative approach where when we look at site, we can determine how much risk or what type of soil it is at site. So in this era, this type of technology is still being developed where we can able to define or identify what type of soil along the slope area so that we can make further investigation into the slope. Okay, so the first part here is see a contour. So this shows a different type of soils at site. Okay, make some analysis and you get this type of contour, different colors. The other one is the technology is able to see which type of area or soil which is at high risk. So if you can look, there are different type of colors. So basically the green one is of safe state and the red is of high risk. Okay, so the advance of analysis in geotechnical engineering will be able to cater a more comprehensive information towards looking at a soil or slope areas. Now this principal approach is simple theory. Okay, if you look at slope, that sliding will occur if shear stress. Now in this condition, shear stress will be considered a negative effect. Okay, now if shear stresses develop in the soil exceed the corresponding shear strength the soil possesses, So shear strength is like something which is a resistance. Okay, so you have negative or a load from the shear stress, and you compare it to the resistance from the shear strength. Okay, now certain practical considerations make precise stability analysis of slope difficult to practice. In the first place, sliding may occur along any of a number of possible surfaces. In the second place, a given soil's shear strength generally varies throughout time as soil moisture and other factors change. Obviously, stability analysis should be based on the smallest shear strength a soil will ever have in the future. This is difficult, if not possible, to ascertain. So, a general information about slope analysis. This is a very beginning part of how you analysis a slope. Now, it is therefore normal in practice to use appropriate safety factors when one is analyzing slope stability. There are several techniques available for stability analysis. Now we're going to look at some of this stability analysis. Now let's move on to subchapter number 2, which is focusing on concept analysis of a mass resting on an inclined layer of impermeable soil. Okay, inclined layer means this part of it. If you have an inclined layer over here. Now one can picture a fairly simple slope stability analysis of a soil mass. So this is a soil mass resting on an inclined layer of impermeable soil. Okay, now let's change this again to highlighter. Now there exists a tendency for the upper mass to slide downwards along its plane of contact with the lower layer of impermeable soil. So this approach is using a straight line, which is the plane of contact. Okay, so that's the first approach. Okay, so you have your mass on top and it's resting on an inclined straight line. Okay, so this figure shows soil mass resting on an inclined layer of impermeable soil. Now the force tending to cause sliding is the component of the upper mass weight along the plane of contact. So it makes sense. Now, by referring to figure E2, so this is figure E2, okay, and considering a unit width of slope, one can compute the upper weight by using the following equation. Okay, so the W is given by this equation, E1, where gamma is the unit weight of the upper mass, hence the force tending to cause sliding is given by the following equation. Okay, so this is the force tending to cause sliding, which is given by equation E2. So you have the weight, W, and you have your force by the weight. And if you were to draw on this, okay, so these are the basics parameters before you derive into this two formulation. Okay, so the basic parameters are in place. You have your angles here, another angle over here upon ABC, and the loading, of course. Now forces that resist sliding result from cohesion and friction. So remember, you have a negative and positive aspect. So this is the positive, means a resistance. Okay, so how do we show this in numeric numbers? Okay, so in quantitative terms, the cohesion component is the product of the soil's cohesion times the length of the plane of contact. Okay, this friction component is obtained by multiplying the coefficient of friction between the two strata by the component of the upper mass weight that is perpendicular to the plane of contact. So in the end, the resistance is calculated as follows. Okay? By considering a parameter from the cohesion and also from the friction. So these two are a good thing in the slope. It's a positive aspect. So the next formulation is derived, which is given by E3. So this is the resistance. Okay. And if you want to look at more details, so where this symbol is the angle of friction between the upper mass and the lower layer of impermeable soil. Okay, so the rest are spell out earlier, just for this angle of friction. Okay, now the product of this is given by factor of safety. Now the factor of safety against sliding is determined by dividing the resistance, which is the positive effect, to sliding force, okay, Rs, by the sliding force. Okay, so you have the first is resistance and second one is the stress. Just divide these two and you get your factor of safety. Okay, so in simple concept, if the resistance is in higher value than the stress, means very good, factor safety will become higher, means more than 1, so it is prone to a safe slope. Okay, whereas if you look on the other way, if you see that the resistance has a lower value than the stress, okay, so when you calculate factor of safety, it will become less than 1. Okay, and this is prone to unsafe slope stability. Okay, so if you want to look at figure E3, so this one gives the formulation required to evaluate L and H, which are needed in applying equation E1 and E4. Okay, so if you want to go more detailed, this is how you calculate the remaining parameters. Okay, pretty simple basic maths, so you can derive this easily. Okay, now we have a table E1, and it gives the significance of factors of safety against sliding for design. Okay, so what does this shows us? Okay, so this is table E1. So significance of factor of safety for design. So if you know that safety factor is less than 1, so your significance is unsafe, as I mentioned earlier. And if your safety factor is 1 to 1.2, it's questionably safe. Okay, if it falls in 1.3 to 1.4 range, it's satisfactory for cut, feels questionable for dams. Okay, and if you get a higher value of 1.5 to 1.75, it's safe for dams. Okay, so table E1 is the significant factors of safety for design. Okay, now let's move on to subtopic E3. Now we're going to look at different type of slope in different type of soil settings. Okay, so this setting is on slopes in homogeneous cohesionless soil. So for different type of soil, we have different approach. Okay, so this is one case of a type of soil. Okay, so when the slope angle beta, so you can see this from your figure just now. Is this highlighted? Okay, it is. Okay. Now, the slope angle of a sand slope, okay, exceed the sand's angle of internal friction. The sand slope tends to fail by sliding in a downhill direction parallel to the slope. Pretty easy. Okay, if B is bigger than the internal friction, so it tends to fail. Okay, now this phenomenon can be inferred by visualizing individual grains of the sand being blocked resting on an inclined plane at the slope angle. So if we want to look more deeper into the soil system, we have the individual grains. Now if the slope angle is increased, okay, the sand grains will begin to slide down the slope when the slope angle exceeds the sand's internal friction angle. Okay, so accordingly, the greatest slope for a freestanding cohesionless soil is at an angle approximately equals to the soil angle. Okay, so this is the greatest slope. Okay, freestanding cohesion. Okay, the slope angle at which a loose sand fails may be estimated by its angle of repose. Okay, the angle formed with the horizontal by sand as it forms a pile below a funnel through which it passes. So you can do a simple experiment here, where you have a funnel, you insert a sand, and you just let the sand passes through, and it will pile. It will create a pile of sand, and the angle is called angle of repose. So what's so important about angle of repose? A sand's angle of repose is roughly equal to its angle of internal friction, as mentioned earlier, in a loose condition, and sand at or near ground surface is ordinary in a loose condition and therefore near its maximum value of internal friction. Okay, this is the concept of angle of repose. Okay. Now the factor of safety for slope in homogeneous cohesionless soils is given by the following equation. So factor of safety equals to tangent of internal friction over tangent of beta. Now clearly, when slope angle beta is equals angle internal friction, the factor of safety is 1. For slope with beta less than internal friction, then the factor of safety is greater than 1. Simple maths. Now let's look at another type of soil. So this is in subtopic number 4. Slope in homogeneous soils possessing cohesion. Okay, so with cohesion more than 0, internal friction equals 0, and cohesion more than 0 and internal friction is more than 0. Okay, now there are two methods are presented for analyzing slope stability in homogeneous soils possessing cohesion. Okay, one is known as the Kalman method, so the first method, and the other is termed as stability number method. So two types of method. Now let's first look at Kalman's method. In this method, the assumption is made that failure sliding will occur along a plane that passes through the toe of the field. So you should know where's the toe, and you should also denote that this is a plane, it means straight line. Such plane is indicated in figure E5. So if you look at figure E5, okay, so this is the such plane. As with the analysis of a mass resting on an inclined layer of impermeable soil, so this one refers to the previous approach, the force tending to cause sliding is given by equation. So it's given by this equation again. Also similarly, okay, resistance to sliding result from cohesion and friction and is given by the equation again. So E3. Okay. And the difference is that it has some additional information here, which is the CD and also this symbol D. Okay, where CD is the developed cohesion and tangent, this is the developed coefficient of friction. Okay, so this is the difference between the earlier approach. So factor of safety due to cohesion, C, and factor of safety due to internal friction denote factors of safety for cohesion and angle of internal friction, respectively. Okay. So as in topic E2, the weight of soil in the upper triangle ABC can be computed by equation E1. So this is one previous approach. But H, the height of the triangle, can be evaluated as follows. So this is a new term in Kalman's method. Okay. And then you do some substituting in E1, so you get another formulation. Okay, and this is the distribution of parameters. You have your H here, B, A, C remains the same, and how the forces is going down here is the same. Okay, the addition is just on this part, okay, where you have your cohesion over here. All right, CD. Okay, the developed cohesion. Okay, and the critical angle, okay, can be determined by equating the first derivative of CD with respect to alpha to 0. Okay, if you go on a step-by-step process, okay, you're going to end up with this formulation, which relates the beta angle and also internal fraction. Okay, and you do continuous substituting, you're going to end up with equation E10 and also E11. All right. Okay. So they have a terms and condition as well. In using equation E11 to compute the safe depth of a cut, one must determine developed cohesion and the developed angle of internal friction by dividing cohesion and the tangent of the angle of internal friction by their respective safety factors. Okay. If the effective safety is caused by the cohesion, it'll refer to this. If the safety factor is due to the internal friction, it is equals to this. Okay, so the Kalman method is gives reasonable accurate result if the slope is vertical or nearly vertical. Okay, as an example, angle beta is equal or nearly equal to 90 degrees. So this fact published by Taylor in 1948. Okay, so that's about E4, which is on Kalman method. Okay, now we're going to move further into stability number method. So as you go further into slope stability analysis, you can see that it becomes more complex because we want to reach an accurate information. So we try to go deeper, and the approach is going to be more complex. So it can be best represent what's the stability at site. Okay, so this is being followed with stability number method. Okay, which assume the failure plane as a circular arc. Okay, previously was a straight line incline. Okay, the previous method, we assume the failure is on an incline, a straight line. But now we want to move more to a good estimation. We assume that the failure surface is a circular arc. So that's the main difference here. Okay. Now, the stability number method is also based on the premise that resistance of a soil mass to sliding result from cohesion and internal friction of the soil along the failure surface. Okay, the same thing. So unlike the Kalman method, again, in this method, the failure surface is assumed to be a circular arc. Okay, so just remember the difference. And a parameter called the stability number is introduced, which group factors affecting the stability of soil slopes. Okay. So the stability number is given by this equation. Okay, and it relates to the height of cut, the cohesion of the soil, and lastly is the unit weight of the soil. Alright. Now for the embankment illustrated in figure E7, so this is figure E7, this is an embankment. Okay. Three types of failure surface are possible. Okay. These are illustrated in figure E8. So this figure E8. Now the first type of failure surface is of a toe circle. Okay. A toe circle failure, which means the failure surface passes through the toe. So if you have a slope, the toe is here. So it passes through the toe. This is the type of failure surface A, which is a toe circle. Okay, let's look at B, slope circle. So this is a slope circle where it is above the toe. This is the toe of the slope. So if it's above the toe, means it falls in the second type of failure surface, which is the slope circle. So let's make things easy here. Let's look at the figure and just explain easily. Okay. And lastly, what does it mean by mid-circle is when you have this type of criteria. The L2 you just divide by half and the slope happens here. Okay, so three types of surface failure that you need to identify in order to proceed with the analysis using this stability approach. Okay, now both the type of failure surface and the stability number can be determined for a specific case based on given values of internal friction and also the slope angle beta. If the value of internal friction is 0 or nearly 0, figure E9 may be used to determine both the type of failure surface and the stability number. So the first case is when internal friction is 0. So an established information is already given to you, so just use it accordingly. Okay, so this is a figure E9. Stability numbers and types of slope failures for internal friction equals 0. So it relates the slope angle, which is beta, and then the ND. Okay, if you refer to the figure, you know what's ND. Okay, and also the type of surface failure, which is given by toe circle with a straight line, midpoint circle with a dotted line, and slope circle with more dotted line. Okay, and the stability number is given here. Okay, just use this established information to go on with the analysis. So these are the step by step, pretty easy. Okay, if you do this, you get this, and then you move further and you get this. Okay, and the last conclusion that we can make is that observation from figure E9 indicates that if the slope beta is greater than 53 degrees, the failure surface is always a toe circle. So if you look at a slope that is bigger than 53, it is likely to be of toe circle. Okay. And if ND is greater than 4, the failure surface is always at a midpoint circle. So this is just observation from published facts. Okay. A general or generic assumption can be made from the figure. Okay. And the list goes on. So if you observe the value of B is greater than 3 degrees, the failure surface is always a toe circle. Okay. Okay, that's all about the observation being done on figure E9. We have another figure which is given by figure E10. Okay. It can be used to determine the stability number for different values of internal friction. So this is when internal friction is not equals to 0. Okay. So the factor of safety for highly cohesive soil that have internal friction equals 0 can be obtained from figure E9 previously. Okay. For soil processing cohesion and having internal friction more than 0, the procedure is more complicated. One procedure is to estimate factor of safety due to the internal friction and determine the internal friction required. Using this value and slope angle, one can find stability number from figure E10. So we have another established information. This is figure E10. Okay, so you have your beta here. So this is beta, please write it down. Okay, and it relates to your internal friction, which has a value which is not 0. If it's 0, you refer to figure E9, but if it's having some values, this is the right figure for you. Okay, so it relates the stability number, the beta, and also the internal friction. Okay, so this figure E10 shows stability number for soils having cohesion and friction. Okay, let's make a conclusion. With this stability number, the cohesion required can be computed from equation E12. Factor of safety due to the cohesion is the quotient of cohesion given divided by C required. So if you look at, if you want to draw a more understandable approach, you just write FSC equals to C given over C required. So that's the formulation. Okay, and if factor of safety internal friction equals to FSC, means Fs internal friction equals to factor of safety due cohesion, the overall factor of safety is equal to, okay, this is what it means. All right, if Fs and FSC are not equal, means factor of safety due to internal friction is not equals to Fs of cohesion, additional values of factor of safety due to internal friction can be estimated and the preceding procedure repeated to determine corresponding value F of factor of safety due to cohesion until the factor of safety is found where these two are equal. So it's kind of a try and error approach. Okay, and you have to make the factor of safety due to internal equals to factor of safety to cohesion. Okay. Now, if the correct factor of safety has not been found after several such trials, means you attempt a lot of trials, it may be expedient to plot corresponding value of both factor of safety on a graph from which the overall safety of factor can be read. Okay, if you have a graph, and then you can just plot the Fs versus Fs, two different of Fs, okay, straight line, and then you can find the equals value, okay, just by using a graph. We're going to stop here for part 1. So please do your design pad to understand more about the previous method before we move on to a more complicated method, okay, which is in E5 method of slice. Okay, right, thank you very much. Stay tuned for part 2, okay, and good night.